Hey friends, today we are going to discuss the entropy flow in open system. Again, this is a topic from irreversible thermodynamics, or it is also known as non-equilibrium thermodynamics. And the second point that we are going to discuss in today's video is the transformation properties of fluxes and forces. So first we will start with the entropy flow in open system. Suppose if we are considering that we have a system which consists two phases, say phase 1 and 2 are these are the two phases which constitutes our system. Now each phase is open and each phase can exchange both its mass, matter as well as energy with one other phase, but the entire system is a closed system and hence only the energy can be exchanged with the surrounding. So we have the two phases or two systems. Now these two systems, they are open with respect to each other, so both this system can exchange matter as well as energy with them, but as a whole both these systems are encapsulated into, or they are encapsulated into a closed system wherein only the energy can be transferred but matter cannot be transferred with the surrounding. Okay, so from thermodynamics we know that the change in the internal energy, or from the first and second law of thermodynamics, the change in the internal energy, that is du, we can write it as TdS minus PdV plus summation gamma mu gamma dn gamma. Okay, where gamma are the number of components which are present in each phases, and all the other terms, they are very well known to us. Now further we can rearrange this expression as we are looking for the entropy production or entropy flow. So basically we will be converting our expression in the form of ds. So we can rearrange this expression. So we will have TdS is equal to du plus, so this I can take on that hand side, this also that hand side. So we will have PdV minus summation gamma mu gamma into dn gamma. Okay, and further from the first law of thermodynamics we know that du we can write it as dq minus PdV, and also we have seen in our previous video that the value of dn gamma is mu gamma into d psi. Okay, so this is our value of dn gamma, and from the first law of thermodynamics we can substitute the value of d mu. So both these values can be substituted over here, and hence our expression, that is TdS, will be equal to, so this we will have dq minus PdV plus PdV minus summation gamma mu gamma into dn gamma. We are substituting it with mu gamma into d psi. Okay, further both these terms will be cancelled out, and this t we can take it in the denominator. So we will have ds is equal to dq by t minus we will have 1 upon t summation mu gamma into d psi. Okay, the value of affinity, that also we have seen in our previous video, that is affinity for a particular chemical reaction. It is written as A is equal to minus summation mu gamma into mu gamma. Okay, so this is our affinity, and this affinity, it can also be replaced. So over here, in place of all these terms, we will be replacing the affinity, and minus minus this will be plus sign, and hence our expression will become ds is equal to dq by t plus a by t into d psi. Okay, so this is our expression. Now as we are dealing with the open system, over here in an open system we know that there is always heat transfer, and as a result the heat transfer, that is dq, dq, we can replace it by d phi, which is represents the energy flow or the heat transfer and the exchange of matter. So in place of dq, we will be replacing it by d phi, as the system is exchanging matter as well as heat transfer is taking place. As the phases are mixing, there are also chances of a certain chemical reaction taking place in each phase. So we must take in account the exchange with the surrounding also, and also as it is a closed system, but there is an exchange of heat in the surrounding, and hence we have seen in our previous lecture that when the entropy is exchanging with the surrounding, it is written as DES. So hence our entropy, which is, or the change in entropy which is taking place due to the exchange, that is DES, we can write it as d phi upon T minus summation of gamma mu gamma upon T and then dE n gamma. So this will be the expression. Now further, this expression we will be substituting it in this particular expression. So our final expression will be, for the total change in the entropy, will be written as ds is equal to, we will have d phi upon T minus summation gamma mu gamma into den gamma upon T, plus we will have a by T into d psi. Okay, this will be the expression. Now this is our general expression. Now when we need to write the expression for both the phases, that is for phase 1 and for phase 2, then in such cases, or for such case, over here we will be writing the superscript 1 for phase 1 and superscript 2 for phase 2, and hence our expression for the entropy, that is ds, it will be d1 phi upon T, 1 is for phase 1, plus d2 phi upon T2 is for phase 2, minus summation of gamma, we can take mu gamma 1 upon T1 is for phase 1, minus mu gamma upon 2 in upon T2, this is for phase 2, and this is dE n gamma 1. So this will remain common, and plus we will have the last term, that is A1 upon T1 d psi 1 plus A2 upon T2 into d psi 2. So this will be the expression, and over here this A1 and A2, they are the affinities of the reaction which is occurring in phase 1 and phase 2 respectively, and this term, that is den gamma 1, it represents the number of moles of component entering the phase 1 from phase 2. So what are the number of components? So this is basically the change in the number of components. So this gives us the change in component which is occurring from phase 1 to phase 2, and similarly the flow of the energy, that is the generalized flow of energy. So this is the general expression. We have seen this the same thing in earlier discussions also, that is d1 phi upon T1, it can be written as dE1 phi upon T1 plus dI1 phi upon T1, which represents the entropy change, or dE phi is when the heat exchange is taking place with the surrounding, and di is when there is an internal heat change. And similarly for the second system, that is d2 phi upon T2, also the same expression can be written, that is we will have dE2 phi upon T2 plus dI2 phi upon T2. Okay, so both these values we will be substituting in this expression, and hence our final expression will become ds is equal to, we will have dE1 phi upon T1 plus dE2 phi upon T2 plus dI1 phi into, we will have 1 upon T1 minus 1 upon T2 minus, we will have summation, and all the other terms will remain as such. So we will have mu gamma I upon Ti minus mu gamma 2 upon T2 dE and gamma 1 plus, and both these terms, so let me write it, A1 d psi 1 upon T1 plus A2 d psi 2 upon T2. Okay, now over here in this expression, this two terms, they represents the entropy flow which is arising when the heat is exchanging between the closed system and the surrounding, because we know that whenever we see dE, then this represents the exchange of heat between the surrounding and the system. So both this term, it shows or it represents the heat exchange, or in the other words we may say that this represents the external entropy change, and the remaining terms, that is remaining all these terms, they represents the heat, or they represents the entropy change or entropy production when there is an internal change, or it represents the entropy production dis. So over here the third term, that is this term, it represents the entropy change due to the energy exchange between phase 1 and 2. Okay, so this term is basically because of the entropy exchanging between the energy exchange between phase 1, because there is a temperature variation. So when the temperature variation takes place, then entropy exchange will take place, and as a result this term is basically due to the energy exchange which is taking place. Similarly, the fourth term, it represents the entropy change which is due to the change in the matter between phase 1 and 2, because we know that over here mu, it is the chemical potential. So this mu is the chemical potential, and this chemical potential, or because of the, we know that when we change the number of moles, then there is obviously change in the chemical potential, and hence there will be change in the entropy, and this term is, or this term represents the entropy change due to the exchange of matter between phase 1 and 2. And the last two terms, that is this two term, it represents the entropy change, it resulting from the chemical reactions which is taking place in each phase. That is over here we know A1 is the affinity, and this affinity is basically because of the chemical reactions which are taking place. So over here both these terms, they have affinity, and both this term, it shows the entropy change which is resulting, or entropy change resulting because of the chemical reactions that are taking place. So hence all the five terms, it represents the entropy production or entropy flow in an open system, and hence we can write entropy production, that is sigma, that we can write it as dis upon dt. This we can write it as di1 phi upon dt into 1 upon t1 minus 1 upon T2 minus, we will have summation of gamma mu gamma 1 upon T1 minus mu gamma 2 upon T2 into dE n gamma I upon dt plus, and we have already seen that d psi upon dt, that we can write it as mu, which is the rate of reaction, and hence this expression will become A1 upon T1 into mu1 plus A2 upon T2 into mu2. Okay, and this all will be greater than or equal to 0, as the entropy of the system is always greater than 0. Okay, so in this particular expression we can see that the each coefficient of rate is enclosed in the bracket. So all these terms which are in the bracket, they are the coefficients, or they are the force terms, and hence the whole expression can be generalized and can be written as sigma is equal to dis upon dt, and that is equal to summation of uh, capital JJ into xj, and that is greater than 0. So this also we have seen, wherein the forces they are denoted by xj and the fluxes they are denoted by jj. So the flow, that is the entropy flow or any flow, it is because of the forces and the fluxes. So gi into xi, and hence the whole thing can be summarized, or they can be simplified and written in the form of sigma dis upon dt and this particular term. So this is all about our entropy flow in an open system. So the next point that we are going to discuss is the transformation properties of fluxes and forces. Basically we are going to see that when the chemical reaction, or when the path of the chemical reaction is changed, are there any difference in the fluxes and forces, or whether the value, that is we have the entropy production, or whether the value of the entropy production it changes or not. So we have seen that the entropy production, that is dis upon dt, is equal to, we have written it as jx, or we for n component we have written summation jj into xj. So we have just seen that. Okay, so over here we know that J is the flux, and this flux is identified as the rate of the reaction, and the generalized force, it is written, or earlier we have also seen that the entropy production was equal to A by T into mu when chemical reaction is taking place. So the flux can be compared with the rate of the reaction, and the general force, it can be compared with the affinity, that is x, we can write it as A by T. Okay, now suppose over here we are considering that a consecutive reaction is taking place. So for a consecutive reaction, we have already discussed the consecutive kinetics of consecutive reaction. So consecutive reaction, that is A gives B, and then B will react to give C. So this is the consecutive reaction that is taking place. Now the affinity of the first, so this is our first reaction, this is our second reaction. So the affinity of the first reaction, we may write it as A1, that is equal, or we can write it as mu B minus mu A, and that we can write it as mu A minus mu B. Okay, similarly the affinity of our second reaction A2, we can write it as mu B minus mu C. Okay, so these are the affinities, and similarly the change in the number of moles of A per unit time, change in number of moles, generally we write it as minus dNA upon dt. So this we can write as new one, which is the rate, or or we can change the sign, and if this will be positive, this will be negative. And similarly the change in the number of moles of C, that is the change or the formation of the product, that is we can write it as dNC upon dt, and that will be equal to nu 2, because this is our second reaction which forms C, so we can write nu 2. Okay, now the change in number of moles of B, so change in number of moles of B, that is dNB upon dt. We know the change in number of moles of B will be the amount of formation of B, and then minus the amount of consumption of B, so that we can write this minus Na upon dt minus, we can write Nc upon dt, and this will be mu1 minus mu2. Okay, so this is the rate of the formation of C, rate of the formation of B. Okay, now the entropy production or the rate of entropy production. Now the rate of entropy production we have already seen from this particular expression. So hence the rate of entropy production, that is T into dis upon dt, the rate of entropy production, this we can write it as A1 nu1 plus A2 nu2. Okay, this also we have seen in our previous discussion, where we have seen that entropy production is, we can write it as summation I ai nu I for coupled reaction. So this is also similar type of reaction, and hence the entropy production, this we can write it as A1 nu1 plus A2 nu2. And similarly, suppose now if we consider that a reaction is taking place, so there is our set of forces and fluxes for first type of reaction. Now suppose if we are considering that the reaction or the reaction is taking a different path and it is going via a different path. For example, suppose if we are considering that we are having a reaction wherein A is reacting to form C and similarly B is reacting to form C. So ultimately for both the steps we are getting the product C, and hence the corresponding, we may say that the affinities, the corresponding affinities for the first and second reaction. Suppose if I write A1 prime for the first reaction, that is A1 prime is equal to, we can write mu A minus mu C, and similarly A2 prime we can write it as mu B minus mu C. So this mu B minus mu C I can write it equal to A2 and mu A minus mu C. So suppose I add both these terms, then BB will be cancelled out, and then hence I can write A1 plus A2. Okay, so these are the affinities, and similarly the rate of consumption, that is dNA upon dt, we can write it as minus nu1 prime. Similarly dNB upon dt, that we can write it as minus nu2 prime, and dNC upon dt, that is rate of formations. Over here in both the steps they are forming, so that will be nu1 dash plus nu2 dash. Okay, so these are the expressions. Now further, when we compare both these terms, that is this term and this term, then we can write that nu1 is equal to nu1 dash, and for nu2 we have v2, and this will be equal to this, so we can write nu2 is equal to v1 dash plus v2 dash. Okay, now similarly the entropy production for this particular reaction, that is entropy production for this reaction, that is dis upon dt, we can write it as A1 prime mu1 prime plus A2 prime mu2 prime. Now this A1 prime I can substitute A1 plus A2, and in place of A2 prime I can substitute A2, and similarly for V1 prime I will substitute V1, and for V2 I will I can rearrange this in the form, that is V2 prime is equal to V2 minus V1 prime. So in place of V2 I will rearrange, or I will substitute this particular term. So our expression will take the form, we will have A1 plus A2 into mu1 plus we will have A2 into mu2 minus mu1, and when we simplify it we will get A1 mu1 plus A2 mu1 plus, and also in place of mu1 prime I can substitute mu1, so we will have A2 mu2 minus A2 mu1. So over here both these terms will be cancelled out, and we are left with A1 mu1 plus A2 mu2. Okay, so hence this expression is similar to this expression, and this is similar to our expression number 1 which we got. Okay, so hence over here we can see that the new set of the equations which are formed the entropy production which we are getting for the new set of the reactions. That is, first we have taken the consecutive reaction, and after that we have taken the parallel or any particular reaction. So in both the cases, the ultimate product formation is we are getting C is the final product, and when the product form is same, then under such circumstances, irrespective of the path that we are following, the transformation properties of fluxes and forces will always be same. Okay, so hence irrespective of the path we are taking, the values of the forces and the fluxes will be same, and thus we can generalize this as, suppose we can write summation of jj into xj is equal to summation of j, we can write j prime j into x prime j. So hence the transformation properties of fluxes and the generalized forces are such that we can take the linear combination of the forces in the new set, that is, we can take the linear combination in the new set, that is new set of forces and new set of fluxes, and hence this relationship holds very true. Okay, so for irrespective of the path that we are taking, the transformation properties of fluxes and forces, they remain same when the final product that we are getting is same. Hope the explanation for both the cases will be clear. Thank you very much.